All right, let's talk about something that's, well, everywhere. It's this silent, invisible force that messes with pretty much every piece of digital information you send or receive. I mean, from a simple text message all the way to a signal from a deep space probe, we're talking about something called AWGN. And you know what? Understanding this thing is absolutely the first step to beating it.
So let me ask you this. What do you think is the single biggest enemy of a clear signal? I mean, seriously, think about it. Whether you're just trying to stream a movie without it buffering or you're an engineer listening for data from Mars, what's that one thing that's always trying to corrupt that perfect transmission?
You know, the answer is so simple, it's almost funny. It's just noise. That's it. It's like the universal static of the universe, this unwanted energy that's constantly degrading, distorting, and just trying to drown out every single message we try to send. Okay, but noise is a really broad term, right? It could be the thermal hum from the electronics inside your own phone, just from the components getting warm. It could be a big burst of energy from a lightning strike, or even just interference from somebody's microwave oven next door. So to even begin to fight this enemy, engineers realized they first needed a way to describe it, a kind of common language to model its behavior. And the most powerful, most widely used model they came up with, that's what we call AWGN.
All right, so let's do this. Let's break this thing down letter by letter and build a complete profile of our culprit. First up, the A. The A in AWGN stands for additive.
Now, additive is probably the easiest part of this whole thing to wrap your head around. It just means the noise doesn't do anything complicated. It doesn't multiply or warp or twist our original signal in some weird way. It literally just adds itself on top. Think of it as just a direct pylon of unwanted energy right onto our clean signal. Simple as that. Okay, let's actually visualize this so it makes sense. Imagine what you're seeing here is our original, perfect, pristine signal. We'll call it ST. This is the flawless message as it leaves the transmitter. Okay, so that perfect signal starts its journey. And as it travels through the channel, and that channel could be anything, a copper wire, a fiber optic cable, even the empty vacuum of space, it runs into this. This is N of T, a totally random, unpredictable noise signal. And here's what you get at the other end. The signal that actually arrives at the receiver, which we call R of T, is just a simple sum of the two. It's our original signal, S of T, plus all that noise, N of T, that got dumped on it along the way. And that right there, that's the entire game for a receiver, to look at this messy, corrupted signal and somehow figure out what that original, clean signal was trying to say. All right, we've got the A down. Next up in our acronym is the W, and W stands for white. And this part of the name, it really describes the character, or you could even say the color of the noise. And the best way to think about this is to remember white light. Back in physics class, you learned that white light isn't actually a single color, right? It's a combination of all the colors of the rainbow, all smashed together at the same intensity. Well, guess what? White noise works on the exact same principle. So instead of containing all the colors, white noise contains all the frequencies with equal power. That's what we mean when we say it has a flat or constant power spectral density. It's basically the ultimate background hiss, just spread out perfectly evenly across the entire spectrum. And this is a huge deal because it means there's no quiet frequency you can just switch to and hide. The noise is everywhere, so engineers have no choice but to design systems that can deal with it head-on. Okay, now for the part that sounds the most mathematical, but stick with me. We're on to the G, which stands for Gaussian. And this tells us all about the statistical behavior of the noise's amplitude. In other words, its strength at any given moment. So let's recap. We know the noise adds itself to our signal. We know its power is spread out evenly across all frequencies. But the big question is, how strong is that noise from one instant to the next? And here's the fascinating part. While the exact value is random, the probability of it having a certain value isn't random at all. It follows a very, very specific pattern, and that pattern is the Gaussian distribution. Whoa, okay, I know, that formula looks pretty intimidating, but trust me, this thing, the probability density function, or PDF, is an absolute cornerstone of communication theory. And here's why it's so cool. It just so happens to perfectly describe the random thermal noise that's created by, get this, the simple jiggling of electrons inside all electronic components. It gives us this incredibly precise mathematical tool to predict the chances of the noise having any particular strength. And if you take that scary formula and just plot it on a graph, you get something you've definitely seen before, the famous bell curve. And what this picture tells us is really intuitive. It says that small, little noise fluctuations, the values right there in the middle of the curve, happen all the time. They're super common. But those huge, powerful spikes of noise, the values way out on the skinny tails of the curve, they're incredibly rare. And that statistical predictability is worth its weight in gold. It lets engineers design systems that are built to handle the noise they're most likely to see.
Okay, we have officially gathered all the clues. We've defined the A, we've got the W, and we've cracked the G. So now let's put it all together and create that complete profile of our culprit, AWGN. So here's the bottom line. When we talk about AWGN, we are not talking about just any old random noise. No way. We're talking about a very specific, mathematically defined process. It's an interference that, 1, adds to our signal, 2, is white, meaning its power is spread evenly across all frequencies, and 3, is Gaussian, meaning its strength follows that predictable bell curve distribution. Additive White Gaussian. That's the whole shebang. But, this raises a really good question. The real world is a messy, complicated place. So why on earth do engineers and scientists focus so much on this one super specific model? Why does AWGN matter so much? Well, it really boils down to 2 huge reasons. First, it's just incredibly accurate. It turns out to be a fantastic model for that fundamental, unavoidable thermal noise that exists in any electronic receiver. But just as important, it's what we call mathematically tractable, which is just a fancy way of saying it's simple enough that engineers can actually do the math. It creates this predictable baseline that lets them design real-world stuff, from simple filters to entire communication systems, and even figure out the absolute theoretical limits of how fast we can send data. It's a game changer.
And hey, don't just take my word for it. As this quote from Prokas and Salehi points out, the importance here is not just theoretical stuff on a blackboard. The AWGN model was absolutely essential for solving one of the first and greatest challenges of the space age. How do you reliably hear the faint, whispered signals from probes traveling across the vast, noisy emptiness of deep space? So, there you have it. We've officially unmasked our adversary. We've profiled its behavior, its characteristics, its statistical patterns. We've built the complete model of AWGN. And all of this leads us to the next and, honestly, the most critical question of all. Now that we know our enemy so well, how do we build systems to fight back and win? Well, that's a story for another explainer. Thanks for tuning in.